So again, we'll just go through some more psychrometric chart questions. We have number 1, the dry bulb temperature of air is 14 degrees Celsius in a room, and we know that the volume is 60 meters cubed. The mass of water vapor in the room is 432 grams, and the mass of dry air in the room is 72 kilograms. The molar mass of water is 18 grams per mole. So we want to find out the wet bulb temperature in the room. So you're going to find so first of all, you need to find out the moisture content in this room. So the moisture content in this room can be worked out from the mass of water vapor and the mass of dry air. Okay, so the moisture content is equal to the mass of water vapor divided by the mass of dry air, and that's going to be 432 grams divided by 72 kilograms, which is 6 grams per kilogram. Okay, so that's our moisture content. So now we can work out the wet bulb temperature. So we have our x-axis, which is our dry bulb, and we're told that was 14. And we're also going to have our y-axis, which is our moisture content. And we know that the moisture content is 6. Right? So then you're going to find the point of intersection. So at this point here is the intersection. And you're going to find the diagonal, because wet bulb runs diagonally. So you're going to find the diagonal line that intersects with this point of intersection. And you will find that that line will be 10 degrees wet bulb. Okay, so this is a little bit harder because there's another step involved, figuring out what the moisture content is. Number 2, what's the partial pressure of water vapor in the room? So this is following on from the first question. We want to find out the partial pressure of water vapor. So remember that the partial pressure, remember our ideal gas law, so PV is equal to nRT. And we're after pressure, so we're going to rearrange this. So pressure is equal to nRT over V. So in order to solve this, we need to find out the number of moles. So we don't know what the number of moles is, but we can calculate it because we've been given the molar mass and the mass of water. So N is equal to mass over molar mass, M over M. Our mass is going to be 432 grams. So because we've got molar mass, which is in grams, we're just going to leave it in grams for this one. Okay, so 432 over 18, and that's going to give you 24 moles. So we have 24 moles of water vapor. P is equal to 24 times 8.3 times the temperature, which is 14 degrees Celsius. But remember, we have to convert this into Kelvin. So plus 273.15, which is going to be 287.15 over volume, which is 60 meters cubed. So that will be 953 pascals. okay, or 0.95 kilopascals. Okay, number 3. We have a greenhouse with a volume of 22 meters cubed at an air temperature of 33 degrees Celsius and a relative humidity of 80%. The greenhouse is sealed and the temperature inside drops to 14 degrees Celsius overnight. So we have a drop in temperature, and assuming that all the air in the glass house is now saturated, so when if they say the air is saturated, it means that the relative humidity is 100%. Okay, so if they say the air is saturated, it means that relative humidity is 100%. How much water condenses onto the inside surfaces of the greenhouse overnight? So what's happening is that right now this air contains water as water vapor, and warm air can hold more water vapor than cold air. So if the temperature in this room is to drop, then the air can't hold as much water as it is right now. So some of it's going to turn into liquid, and that's going to happen on the windows and the walls. So that's why when it's cold you get water forming on your windows, right? I'm sure you've all seen that in your houses. Okay, so that's because the air is getting colder and it can't hold as much water as when it's warm. So we want to find out exactly how much water has condensed or turned into liquid, and we want that in grams, and we've been told the density of dry air. So here we need to find out the initial moisture content. So initial moisture content, you'd have to find 33 degrees on your x-axis, the dry bulb temperature, and you'd have to find the relative humidity line of 80%. So this is the 80% relative humidity line, and you're going to see where it intersects. And the initial moisture content is going to be the Y value. So the height. So you're going to go across horizontally, and this value should be 26 grams per kilogram. So that's your initial moisture content, and your temperature drops so your dry bulb temperature is now 14 degrees. So you now have to find 14 degrees on your dry bulb, and remember that the relative humidity is now 100%. So you have to find the intersection with the 100% relative humidity line now. So this is 100% relative humidity because the air is saturated now. So at this point here, this is now your new moisture content. And if you follow that across, it should be 10 grams per kilogram. So this is now your final moisture content. Okay? And so your change in moisture content is going to be 16 grams per kilogram, and you need to multiply that by the number of kilograms of dry air there is in the room, but we haven't been told the amount of the mass of the dry air in the room, have we? So we need to calculate it. So we've been given the volume of air, And we've also been given the density. So if we have volume and density, we can calculate the mass. So mass is equal to density times volume. So the density of dry air is 1.2 and the volume is 22. So the mass of air is going to be 26.4 kilograms. And so we're just going to multiply 16 by the kilograms of air, by the amount of air. So that's going to be 422 grams of water that has condensed. Okay. So number 4, a fireman fights a fire for 1 hour without ingesting any fluids. Suppose that the fireman evaporates sweat from his skin fast enough to maintain heat balance so that Q body equals 0, and that only 50% of the sweat he produces will evaporate. If the fireman initially weighs 100 kilograms and has a net metabolic rate of 565 watts, so net metabolic rate, that's the total energy that he's using per second, or the total amount of energy that he's burning up per second, and a work efficiency of 10%. So that means that 10% of his energy use is work and 90% will be heat. So we want to find out how much water he'll lose in the hour that he spends firefighting as a percentage of his body mass. And we've been told the latent heat of evaporation of sweat. So first of all, we need to find out how much heat he's going to produce over that 1 hour, because that's the amount of heat that he's going to have to lose, right? Because remember that we're told that he's maintaining heat balance, so he's not, his temperature isn't increasing, so he has to lose the same amount of heat that he's producing. So we know that heat is 90% of the total, and the total is 565 watts. So total is equal to 565 watts, and heat will be equal to 90%, or 0.9 times 565. So that's going to be 508.5 watts is the amount of heat being produced per second, and we have to multiply that by 1 hour. So the total heat produced, so the total Q, which is heat energy, is going to be the rate, which is power, multiplied by the time. So that's 508.5 multiplied by 1 hour, which is 3,600. And that will give you 1,830,600 joules. So that's the amount of energy, heat energy that he's produced. And that's the amount that he has to lose. And he's going to lose that through evaporation. So remember that the evaporation of sweat is what cools us down. So we have the equation Q equals ml. So I went over that last week. It's whenever you have a phase change. So the sweat is going from liquid to gas. So we're going to rearrange this equation for mass. And mass is going to be equal to Q over L So Q is 1,830,600 divided by L, which is 2,430 kilojoules. So we have to turn that into joules. So that's another 1,000. So 2,430,000 joules. That will give you 0.75 kilograms. So 0.75 kilograms of water has to evaporate in order for him to lose that amount of energy. But remember that only 50% of the sweat is going to evaporate, so he's going to have to produce double the amount of sweat. So that's 0.75 times 2, which is 1.5 kilograms. So he has to produce 1.5 kilograms of sweat. And so 1.5 is 1.5% of 100. So your answer is 1.5%. Okay. So that's quite a hard one. But yeah, it just like illustrates some good concepts, like putting together a lot of things. But that's probably the hardest one there is, like out of like the last few years. So don't be like too distraught. Number 5, an Antarctic fur seal spends 5 hours hunting, during which time its metabolic rate increases to allow the seal to do mechanical work at a rate of 150 watts. If the seal has a mechanical work efficiency of 15%, how much energy would the seal need to gain from the food it catches in order to neither gain nor lose body mass while hunting? So what that means is that how much energy, so how much total energy is the seal going to burn in the 5 hours that it spends hunting? Okay, so we need to find the total amount of energy that it's going to use. So remember, total is made up of, so you can calculate the total if you know the efficiency and the work. So the total is work divided by the efficiency. So the work is 150 watts and the efficiency is 0.15 or 15%. So that's just the total is going to be 1,000 watts. So watts, remember, is joules per second. So energy is equal to the power multiplied by time. So 1,000 times 5 hours. So 5 times 3,600. And that will be 18 million joules, which is 18 megajoules. Okay. So a cyclist trains by cycling for 3 hours at a constant rate on a stationary bike. During this time, she does mechanical work at a rate of 100 watts and loses heat to the environment at a rate of 300 watts. After training, she intends to eat enough chocolate to replace the energy she has lost in the last 3 hours. A 100-gram bar of chocolate contains 2,270 kilojoules of energy. So we want to find out how much chocolate she should eat in grams. So first of all, you need to find out the total energy, because you want to replace all the energy that she has lost, and so the total is going to include mechanical work and heat. So the total will just be the work plus the heat. So work is 100 watts and heat is 300. So our total rate of energy use is 400 watts. Okay, and that's happening for 3 hours. So the energy use over 3 hours is going to be the power, the rate of energy use, multiplied by time. So 400 times 3 times 3 times 3,600, the number of seconds in 1 hour. And that's 4,320,000 joules. So in order to find out the number of chocolate bars that she should eat, so this is the number of chocolate bars that she should eat, you're going to divide the total energy by the amount of energy in one chocolate bar. So 4,320,000 divided by the amount of energy in one chocolate bar, which is 2,270 kilojoules. So another 1,000. And that will give you 1.9. So she has to consume 1.9 chocolate bars. And because each bar of chocolate is 100 grams, 1.9 times 100 will be 190 grams of chocolate. Okay. And then number 7, a large freezer has a constant internal temperature of 0 degrees Celsius and sits in a large room which has a constant temperature of 18 degrees Celsius. The freezer is insulated with a 0.2 meter thick layer of polystyrene, and the thermal conductivity of polystyrene is 0.035. And there's a wool layer which is 0.2 meters thick, and the conductivity of wool is 0.07. So the K of poly is 0.035, and the K of wool, the thermal conductivity is 0.07. So the conductivity of polystyrene is half the conductivity of wool. Okay, so 0.035 is half of 0.07. So what that means is that polystyrene is a better insulator, and it's gonna let less heat through. And we want to look for the following, the true statement. So we'll look at option A. The rate of heat transfer through the polystyrene is greater than the rate of heat transfer through the wool-based insulator. So what do people think? True or false? False. False? Yep, it's false. What about B? The rate of heat transfer through the polystyrene is less than the rate of heat transfer through the wool-based insulator. True? This is false. Yeah, so everyone gets tripped up on this one. So basically, we'll say that this is the inside of the freezer, which is 0 degrees Celsius. And then you're going to have your first layer of insulation. So let's say that this is the polystyrene. And And then you'll have your second layer of insulation, which is the wool. And then the room temperature is, so the room temperature is 18 degrees Celsius. Okay. So we said that the polystyrene is going to let less heat through than the wool, right? So the thermal conductivity of polystyrene is lower, and they're both the same thickness. So what's going to happen is that so what's happening is energy, the heat energy, has to go from inside. It has to go from inside and go through both of these layers in order to get, oh sorry, that's the other way, because it's heat going, so heat goes from hot to cold. So the heat has to go from the outside through the wool layer and then through the polystyrene layer in order to get to the inside, right? But the thing is that the rate of heat transfer through both of these layers has to be equal, because it's like a traffic jam. If you imagine that this was a bridge and you had cars on this side, and if this one was slow, if this bridge had a traffic jam on it, eventually the cars could only go through at a rate that they could go through this bridge, right? So it all has to, it's going to go at the speed of the, sorry, let me rephrase that. So it's going to go at the rate of the slowest one, which is going to be the polystyrene. Okay. So what that means is that the rate of heat transfer through the polystyrene will be equal to the rate of heat transfer through the wool. Okay, so there's the same amount of energy passing through the wool and passing through the polystyrene. Okay, and so what's the difference going to be? The difference is going to be the difference in temperature across this layer. So this side of the polystyrene and this side of the polystyrene will have a greater temperature difference. So the delta T of the polystyrene will be greater than the delta T of the wool. Okay. So let's say, for example, this inside layer, so the air in between the polystyrene and the wool could be, let's say, it would be 12 degrees Celsius, right? So the difference between the inside and this side is going to be 12 degrees, while the difference between this side of the wool and this side of the wool is going to be 6 degrees. Okay, so do you get that? So if you did, so delta Q over T is equal to H times A times delta T, right? So it means that because the delta Q over T of both, the rate of heat transfer of both is the same, we can rewrite this as the H of polystyrene multiplied by the surface area of polystyrene multiplied by the temperature difference across the polystyrene is equal to the H of the wool multiplied by the surface area of the wool multiplied by the temperature difference across the wool. Okay? And so we know that the area of the polystyrene and the area of the wool has to be the same. Okay, so these are going to cancel out because the surface area is going to be the same. So we know that the conductivity of the polystyrene is half of the conductivity of wool. So if this is half, in order for both sides to be equal, this one's going to have to be double, right? So that's what we've found. We found that the temperature difference across the polystyrene is 12 degrees Celsius, whereas the temperature difference across the wool is only 6 degrees Celsius. Okay, so that's really important to remember because that's going to be fundamental to you guys solving these problems. The rate of heat transfer through each layer is always going to be the same. And the difference is going to be the difference in temperature across those layers. Okay, so see, the temperature difference across the polystyrene is greater than the temperature difference across the wool-based insulator. So this is our answer. This is true. D, the temperature difference across the polystyrene is less than the temperature difference across the wool-based insulator. No, this is false. The net heat transfer rate depends on whether the wool-based insulator or polystyrene is on the inside. So it doesn't matter whether the wool's on the outside or the wool's on the inside, which order they're in. It's always going to be the same across all the layers. Okay. All right. Number 8, a student has a skin surface area of 1.2 meters squared and a skin temperature of 25 degrees Celsius. He's wearing 1 millimeter thick polyester clothes, and the surface heat transfer coefficient for radiation and convection from the surface of his clothes is 25 watts per meters squared per Kelvin. What's the rate of heat transfer from his skin through his clothes to the outside air if the air temperature is 5 degrees Celsius? All right, so we'll write down the variables that we have. So for these ones, these types of questions, they usually don't give you like anything that you don't need. So you can just write down all the variables that you've been given. So area is equal to 1.2 meters squared. The skin temperature is 25 degrees Celsius. And the outside air temperature is 5 degrees. So that's a difference, a delta T of 20 degrees Celsius. And the thickness of the clothes is 1 millimeter. So that's D. D is equal to 0.001 meters. And the surface heat transfer coefficient, so that's H of surface, is 25. And we want to find out the rate of heat transfer, so that's delta Q over T equal to question mark. And we know that the K, so the thermal conductivity of polyester, is equal to 0.05. Okay, so we need to find H total. So first of all, we're going to find the H of conduction. The H of conduction is equal to K over D. So K is 0.05 divided by the distance, which is 0.001. So that's going to be times 1,000, so 0.5550. So 50, and then in order to find the H total, we need to add the reciprocals. So that's H of conduction to the power of -1 plus the H of surface to the power of -1, and all of that to the power of -1. So that's 50 to the -1 plus 25 to the -1. So that's going to be 16.667 is our H total. And so delta Q over T, our rate of heat transfer, is equal to H total times the surface area times the difference in temperature. So that's 16.667 times our area, which is 1.2, times our difference in temperature, which is 20. So that's going to be 400 watts. Okay. All right. Okay, so number 9, we have an Arctic fox with surface area of 0.2 meters squared and a core body temperature of 38 degrees Celsius, and it has a 1 centimeter thick layer of fat and a 4 centimeter layer of insulating fur. If the outside temperature of the fox's fur is -5 degrees, then what is the skin temperature of the fox? So this one's another really hard one, but I've got 3 questions that are exactly the same, but just with different numbers and like situations. So hopefully by the end of it, you'll kind of get it, or at least know how to do it, even if you don't understand it. So the body is 38 degrees Celsius. And then we have our first layer. We have our first layer of insulation, which is the fat. So this is the fat. And it's 1 centimeter thick with a K thermal conductivity of 0.2. And then between the skin and then after the fat is going to be the skin, because the fat's right under the skin. So we want to find out the temperature of the skin, so we'll call that T skin. So T skin is equal to question mark. And then on the outside of the skin, we have our second layer of insulation, which is the fur. So this is the fur. And then on the outside of the fur, we're going to have the air. So the air is going to be -5 degrees Celsius. Okay. So we're going to calculate the H, the heat transfer coefficient of the fat. So H fat is equal to K over D, which is going to be 0.2 divided by 0.01, so 1 centimeter. So the H of fat is going to be 20. Okay. And then the H of fur is going to be 0.16 over 4 centimeters, which is 0.04. And that's going to be 4. Okay, so we know the H of fat and the H of fur, so I'm just going to tidy this up a bit. So you calculate H by using K over D, so that was 20, and this is 4. Okay, so we've got the H of fat and the H of fur. So we want to find out the temperature of the skin in the middle of these two layers. And the concept that you have to know is that the rate of heat transfer through these two layers are going to be equal. So that means that delta Q over T through the fat is equal to the delta Q over T through the fur. Okay, and remember that delta Q over T is equal to HA delta T. So H of fat times the surface area of fat times the temperature difference across the fat is equal to the H of fur multiplied by the surface area of fur multiplied by the temperature difference across the fur. Okay? And we can assume that the surface area of the fat is equal to the surface area of the fur, so we can cancel the surface areas out. And then, so here, we don't know delta T, so we need to replace delta T with T outside minus T inside. Okay? So we're going to replace delta T with outside minus inside. So that's going to be, so I'm going to get rid of this as well. So for the fat, the outside of the fat layer is going to be the temperature of the skin, right? So T outside is T skin minus, so the inside of the fat layer is going to be the body, so that's temperature of the body. And we'll do the same on this side. So replacing delta T with T outside minus T inside. So for the fur layer, the outside is going to be air, the temperature of air, minus the inside of the fur layer is going to be the skin, so that's going to be T skin. Okay, so now we'll put in our numbers. So H of fat is 20, the temperature of skin we don't know, so we'll leave that as T skin, minus the temperature of body, which is 38. So here, because this is part of delta T, we can just leave it as Celsius. We don't have to turn it into Kelvin. So H of fur is 4, and the temperature of the air is -5, minus the temperature of the skin, which we don't know. Okay. So that's, we're going to multiply 20 times T skin and 20 times -38. So 20 times T skin minus 20 times 38, which is 760. And then 4 times -5 is -20. And then 4 times negative T skin is going to be 4 times T skin. And then we're going to add 4 T skin to this side, so that's 24 T skin. And then we're going to add 760 to this side, so that side's going to be 740. Okay, and then divide both sides by 24. So T skin is equal to 30.8 degrees Celsius. Okay. All right, so next one. So our next one, we have a flat and we have a wall. The wall has an inside temperature so we have a wall. This is our wall. And the inside temperature is 20 degrees Celsius. So we'll say inside 20 degrees Celsius. And then, so we want to find out the outside wall temperature. So we'll call this wall, outside wall. So the temperature of the wall equals question mark. And then so here we've been given the heat transfer coefficient of the surface, right? So what you can do is you can treat the surface as another layer. So you have to treat the surface as another layer. It's not really another layer, but in order to solve our equation, that's what we have to do. So we have another layer, which is the surface. Okay, and we know that the H of surface is equal to 8.1. And we're going to have to calculate the H of the wall. So H of wall is going to be equal to K over D. And K is 0.7. And the thickness is 270 millimeters, which is 0.27 meters. So that will be 2.5926. Okay, so that's the H of wall. And again, remember that the rate of heat transfer through the wall will be equal to the rate of heat transfer through the surface layer. Okay, so H of wall times area of wall times delta T, the difference in temperature across the wall, is equal to H of surface multiplied by the area of the surface multiplied by the temperature difference across the surface. Okay, and again, the area of the wall and the area of the surface is going to be the same, so that can cancel out. And then we have to replace delta T with T outside minus T inside. Okay, so again, we'll do that. So for the wall, the outside is going to be the T wall. T wall, and the inside is going to be the inside wall temperature, which is T inside. For the surface, so we said, and then the air temperature on the outside was 4 degrees. So air temperature was 4 degrees Celsius. So the outside of the surface will be T air minus T wall, which is on the inside of the surface layer. So that's 2.5926, and T wall is unknown. T inside is 20, and that's equal to H of surface, which is 8.1, times T of air, which is 4, minus the T of wall. Okay, and then that's 2.5926 times T wall, and then multiply 2.5926 times negative 20, which is negative 162. So 8.1 times 4 is 32.4 minus 8.1 T wall. And then gonna put the T walls together and then the numbers together. So it's 10.69. T is equal to 194.4, and divide both sides by T. Divide both sides by 10.69.
Wait,
Yep.
Where did the 162 come from? Yeah, 2.59 times 2 is 51.85.
Wait, what have I done? 2 point. Oh yeah, sorry, I must have made a mistake. What is it again? 51.852. Yeah, well, I've made a mistake there then. Yeah, because I was rushing this, sorry, just before I came here. So yeah, that's how you do it. So you can do the rest of the steps and you should get the right answer. But this is all just, you guys should know how to do this from there. So I'll do the last one. So again, it's the same type of question, just another scenario. And this time we've got a penguin with a surface area of 0.4 meters squared, skin temperature of 10 degrees Celsius. The penguin has a 1.5 centimeter thick layer of insulating feathers, and the surface heat transfer coefficient from the surface of the feathers is 8.1 watts per meter squared per Kelvin. If the air temperature is negative 15 degrees Celsius, what's the temperature of the outer surface of the penguin's feathers? Okay. So the skin is 10 degrees Celsius. And then you have your layer of insulation, which is the feathers. And then you have the temperature of the outer surface of the feathers, which you want to find. And then you can treat the heat transfer coefficient of the surface as another layer. And you know that the air temperature, so air temperature is negative 15. So air is negative 15 degrees Celsius. Okay, so this is what we're trying to find. And h of the feathers is equal to k over d. So that's 3.333. And the h of the surface is equal to 8.1. Okay, and again, the rate of heat transfer through the feather layer is going to be equal to the rate of heat transfer through the surface layer. So we're going to use the same equation as before. So h of feathers, and again the surface area is going to be the same. So those will cancel out, and I won't bother writing it this time. And it's going to be T outside minus T inside. And so the outside of the feather layer is the T outer, which we don't know, minus the inside of the feather layer, which is the skin. So that's T skin. And that's equal to the H of the surface multiplied by the temperature, the T outside, which is the air, so T air, minus the inside of the surface layer, which is T outer. Okay, so then we're going to put in our numbers. So 3.333 times T outer minus T of skin, which is 10, is equal to 8.1 times negative 15 minus T outer. Okay, so I'm just going to write down the numbers. 3.333 T outer minus 33.33 is equal to negative 121.5 minus 8.1 T outer. And so then 11.433 T outer is equal to negative 88.1667, and divide both sides by 11.433, and you'll get an outer temperature of negative 7.7 degrees Celsius. Okay, yep.
Do you have any tips for composing that sort of diagram layout, like from the question?
Well, it's just being able to recognize the question. Yeah, so, like, because I mean, this has come up 3 times in the last few years. So, I mean, it's pretty likely that you'll encounter it again. So, yeah, and this is like the hardest one that I think, like the hardest one that you can get in terms of like the heat transfer one. So if you know how to solve this one, then you'll pretty much be sweet, I think. Yeah.
So when you're creating each layer, do you sort of just do it in the order that they state them in?
Yeah, well, it depends on how they write the question. So sometimes if they're nice, they'll write it in the same order. But you have to be able to figure it out yourself. Like that's where it's just useful to do the past exam questions, because then it gives you practice at kind of recognizing what should go where and what's important and what isn't. Yeah, but it's just kind of like experience and practice. Yeah, you can't really just say do this, do that, because you never know what's going to come up. Yeah. All right, cool. Thank you. I'll stick around for a few minutes if you guys have any questions. All right. Thanks.
Must be above the
Goes right there.
Not there.
Why not?